All right, we're going to get started, guys. Welcome to Objects Everywhere. We're going to be talking about some OO stuff we can do. I'm Devon Fritz. I'm a project engineer at DMC. I study at Rose-Hulman, and I have a BS in mechanical engineering.
And Batsche, I'm a project manager at the DMC Chicago office. LabVIEW architect, been working with LabVIEW for 8 years or so.
So, DMC is, this is just going to talk about our company a little bit. DMC is 5 offices across the U.S. We're based out of Chicago. We do test and measurement among some other things in our company. We have a large number of architects and LabVIEW developers. We're a project-based company, so we work in a lot of different industries day to day. And so today, we're not going to be teaching object-oriented concepts. We're going to be more talking about tips and tricks you can do to make your life easier when developing an object-oriented. We're not going to be showing applications specifically or case studies about object-oriented projects. Again, practical habits that can make your life easier. So we kind of boiled it down to 7 different topics, starting with design patterns. That's just going to kind of set the baseline for what OO can be used for in your projects. So NI has published kind of 3 patterns: factory pattern, command pattern, and decorator pattern. These are more paradigms of how you can use OO. They're not restrictive. You can do a lot of things with OO. These are just some good examples. So to start, factory pattern. You can use the factory pattern is showing how you can plug in different hardwares very easily using object-oriented. So on the left, you can see you're dynamically loading a class. This is representing like a hardware driver, and it's casted as a generic plugin. So on the right, you can see that you have your driver, which is your parent class, and specifically you can have like a DACMX child class, and so you could load that up. Or alternatively, it could be another specific driver for whatever hardware you're using. And so ideally, you could actually load it dynamically and plug it in, so to speak. The command pattern is a way to do producer and consumer architecture using class private data to send your message. Some of the difficulties with doing producer and consumer is on how to bundle your message data together. Object-oriented makes that pretty easy to do that, because you have your class private data to bundle your data, and then you have methods that you can call on that data. So on the left, you have your block diagram. Simply, you configure your message by writing to the class private data, you enqueue it, and then your consumer consumes it with dequeuing it and running a dynamically dispatched execute BI. On the right, you can see a sequence element as a generic parent class and 2 child classes, execute action and comment, that are overriding the execute method to perform a certain consumed action. The decorator pattern uses other classes to decorate the class private data. The prime example of this is actually a car example. You have a car, and it can have a powertrain. The powertrain has an engine and a transmission, and it keeps going down and down, lower and lower for each of your parts. And it's kind of a containment hierarchy, we like to call it, and it allows you to extend your functionality as you develop. If you want to implement a specific class later in the future, your classes can be generic enough to override and inherit your generic classes and decorate your main class. In this case, it's a dark roast.
Can I ask a question?
Sure.
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 So does that mean each class is getting added to the private data of the next class?
Yes.
Okay.
So it decorates it. So talking to this specifically, you start with a dark roast, and there's a condiment class, And then their child classes Milk and Mocha, and they get decorated into the class spread data. Oh, sorry. Backwards. So the caveat with those three specific patterns is a lot of those are using three features of object-oriented. Most of the times you're using a lot of the features in object-oriented, so there's kind of a combination of all those patterns or paradigms in your application. So it's not restrictive at all to actually design in those patterns, but it's just showing specific examples of how to do that. So Jesse will be talking about kind of a generic paradigm or inheritance paradigm on work we did at DMC.
All right, so to give a little bit of perspective on what we're going to be talking about. If you want to build a room with a really great view, you could start off by pooling a huge amount of engineering resources and time and technical knowledge, and you could build the world's tallest tower from the ground up to get an amazing view of surrounding areas. You could also take an approach where you invest a much smaller amount of time and resources in a simple design and build a very simple house. But if you are doing that effort on what is an astounding foundation, then you still get the same amazing view that you're going for, but with a much smaller amount of effort and investment of resources. So what we're going to be talking about here is really about establishing solid foundations in software development. And of course, you do this all the time with building up hierarchies of sub-VIs and higher level VIs and trying to develop reusable code. But LabVIEW, of course, provides constructs that make this somewhat easier to do in a very structured way. And so we're going to be talking about inheritance. Of course, it's a core concept of OO, but we're going to be looking at that in a way, as a way to establish these foundations that make development of child classes for a particular application much easier. And as a use case, to kind of give context to this, we're going to be looking at a use case of when you're using object-oriented development for managing configuration data. So what do we mean by that? Well, we can take NIMax as an example that's very familiar to everyone, where you really have a tool to manage the hardware level settings for an application, but NIMax is inherently doing this in an object-oriented way. You have different types of objects that you can configure. You can have tasks, you can have channels, you can have devices and scales, and each of those are different objects. They have unique properties and options that are available based on the type of the object. There's also levels of inheritance. You can have different types of scales, linear scale, polynomial scale, and associated with each of those are unique properties for configuring a linear scale or polynomial scale. So there are child classes inherent in this. And so NIMax is an example of what we're talking about with using LabVIEW OO for configuration data. But we're going to talk about ways that you can develop custom code to do that same type of thing, but for whatever you need for your application. And a good mechanism for doing this and kind of building that foundation is the development of a base class. So this, of course, is a common idea in LabVIEW OO, and there's no right way to build a base class. The right way to do it is in whatever way is necessary to build the foundation that you want for your application. But we're going to look at an example and a few things that might make sense. This is an example where we chose to make a base class. It proved to be very extensible. We got a huge amount of bang for our buck and return on investment in this approach, and we're going to use that as a little bit of an example of things you would want to consider when creating a base class. So of course, any class you start with is going to inherit from the standard LabVIEW object, which doesn't have any data or any properties of its own. And so if we kind of consider DMC object to be this generic base class, we're going to examine what could go in there. So first off, with this base class, it's not going to be abstract in the traditional sense, because it's not just going to be empty with methods that don't do anything. We're going to try and encapsulate functionality here to build it up as a foundation. We will maybe consider this concept of a base class to be abstract in that we wouldn't actually instantiate it and work with instances of it. You'd always create children that do some specific job in your application. So what type of class private data would maybe make sense to go into a base class? The first and perhaps most important thing that we found really made a lot of sense was to put a unique identifier in this base class. This is something that would arbitrarily just refer to this particular instance of an object uniquely and allow the powerful ability for one object anywhere within your application to distinctly reference another object. So what do we mean by this? Well, if we go back to the NIMax example, you have the ability to associate a scale with a channel. And there's a reference relationship there. This is different than talking about memory reference. This is just a relationship where one object is associated to another. A scale is assigned to a particular channel. And you want to have a case where you could rename that scale and choose a different, better name or reconfigure it, but still have that assignment relationship and that reference of what channel is associated with what scale stay intact. Yeah, question?
Does that UID change each time the object is instantiated?
So the idea would be once an object is instantiated, it is given a UID at instantiation, and that stays the same for the life of that object. I mean, you can change the properties of that object or use it in different ways, but the UID stays the same. And that's very important to keep references to that object.
Consider wrapping the class inside of a DVR to accomplish that purpose?
Yeah, so then you're kind of doing by reference, you're referencing a class, but what we're aiming here, so our use case here is using LabVIEW 00 for configuration data, and when it comes time to maintain these references when you go to maybe store this configuration to disk, then having it in a DVR doesn't really work. You need an actual data representation of that, and that's where the UID would come into play. So this idea of establishing these relationships is very similar to if you've worked with a database and had a relational database where different records have primary key and foreign key relationships, and you have relationships between different entities. That's the same thing that we're trying to do here with the UID. And then, as somewhat less important but supplementary properties that are very generic and might make sense, you could have a name, any type of user-facing name for the object. Important idea would be you could rename the object while maintaining the UID-based references to other objects. And then maybe a description that just tended to make sense for us as a way to allow users to provide extended, longer descriptions or comments about the purpose of that particular object. So, in addition to class private data, it's also going to be valuable as part of this foundation to implement base class methods that are broadly useful. And so, this is a list of some that, especially in the context of LabVIEW 00 for configuration data, proved to be useful. We're going to talk a little bit about these. So starting with this idea of a configure method. So if we're going to be using classes for managing configuration data, we need to be able to configure that data. And so we'll start with talking about a method to do just that. Basically, it'd probably be convenient to lay the foundation for any child class that you create to be smart enough to configure itself. And what would this look like? Well, it might look like what we're showing here, where you have a general purpose VI where you can take anything that inherits from your base class, maybe in this case it's a scale, and just wire it into a VI that presents the user with configuration screens for that type of object. So with this relates to our NIMax example, where you can click on a particular object, and based on the type of that object, you get a panel where you can configure the relevant properties for that object. This is familiar to everyone. If you click on a linear scale, you get a panel that looks like this. If you click on a table scale, you get a different panel with different properties that are relevant to that. Similarly for, of course, different types of scales. So this can all be accomplished just by writing and creating your own UI for every child class you create. Whether it's a linear scale or a polynomial scale, you can create a UI that looks just like this, and you can use dynamic dispatch on this configure method to call that UI. That does the job just fine, but again, going back to the house on the mountain picture, we are talking about using a base class to build up foundations. So, if we're just using dynamic dispatch and programming this at a child level, you're not really gaining a lot of functionality in the base class. So it might be nicer if we could program a more general purpose UI that could give a consistent user experience to configure any type of object. And if we only had to program that once at the base class level and could let other child class objects that you create in the course of your application rely on this, then you'd have a nice consistent foundation. It would probably save some development time and add convenience through the course of the project. So a UI that is very broadly usable for configuring objects could look something like what's shown on the right up here. Could be a listing of the properties that that object has available for user configuration, a description to say what that property means within the context of that class, and then showing what the current value of that is. So if that's our goal, we are going to still need the child class to do a little bit of work. And the idea for that is the child class is going to be the only entity that knows what configuration in general what configuration should mean in the context of that class. But we want to minimize the work that those classes have to do to plug into this configuration framework. They need to do the bare minimum to provide their class-specific information, but do so perhaps only by overriding a couple simple base class methods. And so really it boils down to a couple base class methods that would be needed to support this overall configuration framework. The first would be what we call a get properties method, and this establishes the idea that a child class should be able to provide information on its own user configurable properties. Then secondly, a class should have a configure properties method where it determines how a given property of its own should be configured. Again, this is the idea of making child classes provide the information that is unique to them, because that can't be captured at the base class level. They have to do that work themselves. So these two simple methods could be overridden by your child classes. And with that, you could program a UI that was like that general purpose UI with an overall logic flow like this. This isn't a functional, runnable block diagram. It's meant to be somewhat abstract for process, just to illustrate this point. So the idea is that UI, all it would really need to do is take in any object that adheres to this base class framework, run that get properties method. It gets information, it's that pink array of clusters right there, information about the properties for whatever class was wired in. In this case, it happens to be a scale, but anything that inherits from this framework. Could populate what we had as a list box or some general indicator of those properties, and then as long as that UI is open, allow the user to select a property. When they do, call the configure property method, where that child class gets to say what it means to configure it. Do you have a question?
Yeah, you're using a cluster as a placeholder for the properties, not invariant.
You could do either one. Basically, in our case, this cluster was kind of just metadata. It was really the high-level property name, description, and value that needs to be provided by the child class. So just enough to display to the user what the properties are and what their current values are. So then the user can just select properties, configure them, and in the end, when someone clicks OK on this general purpose dialog, you would have the updated class object be wired out with the user configured class data. And so if you use those properties or those general methods as a framework, then you can end up with a UI that will provide the ability to allow any child class to be user configurable, where you don't really have to program a custom user interface to do that. So let's see. So that's looking at the idea of configuration. Then once users are able to configure classes, another base class method that it would be worth considering is a compile method. So what types of things would we be aiming to accomplish with this? Well, we're all familiar with the LabVIEW error list. And when you write LabVIEW code, LabVIEW is doing two things consistently for you. It's evaluating the code you have on the block diagram to determine if it's valid and enumerating and describing any issues that exist. It's showing you the errors. And we also know that LabVIEW has just-in-time compilation to constantly generate compiled code so that you're always able to click the run error as long as your code has been able to compile without any issues. So looking at that block diagram is a configuration for your VI. When you're using LabVIEW OO for configuration data, you might want to do some of the same things. Basically, you have these objects that represent application configuration, and you would want to ensure that everything has a valid configuration. So some level of error checking or integrity checking to make sure whatever the user has entered is valid and actionable. An example of what this might mean is if you have some object that's configured to take a reading from, say, it's just a global virtual channel called thermocouple 4, And that's what the user has selected or entered, but you're able to check your NIMax configuration and say that channel doesn't exist, or isn't defined. Well, then that object is expected to not operate correctly at runtime because it's referring to a channel that doesn't exist. So this is the type of thing you could check as far as error checking in your compilation method and notify the user of this ahead of time versus just having things not work at runtime. Also, much like actual compilation in LabVIEW, you could do steps in this compilation method to prepare things for efficient runtime execution. So an example of this would be if you had a variable object with a formula and you wanted to do the string formula parsing ahead of time to create a compiled version of that could run effectively and efficiently at runtime. You could do that pre-processing up front during this compilation method.
Yeah, we have a question.
Question? Yeah.
What kind of data types do you handle for your configuration of parameters?
You can put whatever you would want in class data. The class, a child class, can have whatever it needs to in its own class data. You would just have that class be able to describe those properties as far as what they mean and format their values generically in a string. That would be the job of the child class.
And then like composite things, like if my class has maybe a cluster that has 100 elements and lots of clusters inside of it,
Mhm.
can we handle that?
Yeah, so the idea there is that's why there's this configure property method that is overridden at the child class level in this example, because then when you have a complex data type like that in a child class, it gives that class the ability to say, what does it mean to configure this? And maybe it is a custom UI where you let them edit this array of clusters, and that's arbitrary and unique to this child class. And so you could say that when you go to configure super cluster array property, then it's presenting this UI that is implemented uniquely at the child class.
Yeah, we have another question.
Yeah.
Do you support persisting the configuration to disk?
So
So you
yes.
can load it on the next run?
Yes.
How
So
do you do it?
that will be the next two methods after compile. We'll talk about the save and load methods for exactly that purpose. So very good question. So if you choose to implement a compile method, a very nice thing that you end up with after taking this through to completion is the idea that you could have many objects and even objects containing objects and iterate through those, compile kind of iteratively or hierarchically through that LabVIEW OO construct and end up with something that looks a little bit like the LabVIEW error window, where you get a listing of compilation notifications, descriptions of the issue, maybe a call stack of where that issue was detected, and then you can run it through this framework where, since everything is part of this base class framework, anything can be compiled for this error checking, and then you generate a kind of listing of what those issues are. And then move on. Another point would be that when you're doing a base class, it doesn't just have to be one all-encompassing base class. You can have different levels of kind of foundational base class structure. We came across a case that we wanted a more intuitive way to manage groups of objects. And so LabVIEW provides arrays. These are fundamentally index-based, of course, but other programming languages have nice constructs such as a dictionary or collection where you can refer to objects by maybe a key or some type of tag. And we wondered if we could do something similar with LabVIEW, and the answer is, of course, we can. We can do something like making this DMC object library class, which is what we're kind of showing on the bottom here. And what is this going to be? Well, it's really just a collection, a dictionary, a grouping of the fundamental base class, DMC object. And the nice thing is there's objects. DMC objects can be anything, any particular child class. So it ends up with a flexible framework that lets us kind of generally manage any group of associated objects. And of course, collection or dictionary constructs are a group of associated values where each value can be referenced by a unique key. So it's a list of key value pairs. We noted earlier that the DMC object was going to have this UID property, and that's really an ideal thing that lends itself well to looking up objects within a dictionary. So with this, the library would have maybe a couple very valuable methods: the ability to get an object by its UID and set an object by its UID. And it just becomes a nice way to manage a grouping of LabVIEW objects. Again, the whole topic of this is managing complex OO hierarchies. You can have a grouping of objects where they're referenced by UIDs. That lets you maintain this referential relationship between maybe it's a channel associated with the scale and a channel associated with the task, and different levels of referencing where those are also parts of groups or libraries of similar objects, and you can find efficient ways to index these things by a string identifier in the background. We chose to use the old LabVIEW variant attribute trick. It's fairly efficient even as the number of objects grows large, and does a nice job of providing that with a simple implementation. So that's talking about a couple base class methods. Any questions on that configure or compile method before we move on to talking about save and load methods? Okay, so here we're going to be focusing a little more specifically on base class methods that deal with the contents of class private data. So these are going to be dealing with the question that was raised of, well, the user has just configured all of this important information and captured that data in a hierarchy of LabVIEW classes. And now for that to be useful in the context of configuration data, we need to be able to save it to disk after it's configured and store it for later, and then load it back up when we want to load a particular configuration into our application. So to make this all work, there are going to be a couple key concepts that we're going to explore to kind of make this able to happen. The first is serialization, and the second is mutation history. So serialization is the idea that we need to be able to take class data and convert it to a format that's easy to store to disk. And this is going to be the basis for these save and load methods. We have some simple, these really boil down to something fairly simple, and we're just going to show what we found to be the best, most flexible tools to accomplish this. So saving is a combination, an addition equation of two simple things. You can take the object itself and use the flatten to XML LabVIEW primitive to break that down into an XML string, and then you just need to write that string to an XML file. LabVIEW provides a native write to XML file VI, which would do the job. We chose to use GXML. They have a very similar write XML to file VI, and they do essentially the same job. We just point out that GXML has the nice feature of being RT compatible, whereas the NI primitive, for whatever reason, is not RT compatible. And so that was something we needed to support. So we chose to use that. So really, you have an object that you want to save disk, you convert it to XML string, you take that XML string, write it to a file. Very simple. Loading is the inverse process. You know the file where this is stored, you read the XML string out of that, and then you simply use the unflattened from XML VI to convert that, basically parse that back into an object. There are certainly other formats other than XML that you could break the class down into and store it to disk. Why do we choose XML particularly? Well, the reason is that XML, and particularly these flattened to and from XML primitives, allow us to take advantage of class mutation history. And so that's going to be the next topic. This is a very important thing that provides great advantages in managing configuration data. And yes, question.
Does the load method actually read that XML string from a file?
Yeah, so the first thing in the load, right after the load, would be simply file IO to take the file path where this is stored, a path to an XML file, and to read in the corresponding XML string, which is just going to be a big long
So the
string.
question is, this is good for one project. On a different project, you need to write those strings to a database. This method wouldn't do it, right?
No, so this is talking about, I guess you could write those XML strings to a database. It's a very large
Yeah,
string.
but this specific method wouldn't do it because it doesn't have any URL to the database.
Right, that's true. So
So
then,
how do you deal with this situation? Changes in requirements from application to application, where to store your configuration.
yeah, so you would just, basically, you could implement base class another method. Perhaps it should actually be called save to file and load from file. And you could similarly have a save to database and load from database, where you could still decompose the class data in a similar way, but instead of taking that broken down data and storing it to an XML file, you
Yeah, but you're
could use
getting a
database.
tab interface for your base class. This is not good.
That's true. So this certainly isn't covering everything across the board. And if you were working with the database, you would, yeah, you could create different levels of base classes and accommodate both.
You were presenting on Agile Zone, correct?
Yeah.
Yeah. Okay. Is that
Do
what
you
you're?
guys do practice solid principles?
What was that?
Do you guys use solid principles to design your software, your class hierarchies?
Do you mean that specifically?
Solid, yeah. I don't-
Oh, as referencing your presentation.
This is a violation of the single responsibility principle.
Okay.
I
I think you do have a good
Explain it
point.
later. I
Okay.
don't want this to overlap.
We'll talk to you.
Yeah, I think that's a good point. I mean, this was a little bit application specific, so we're trying to point out a few. But I think you're very valid that there are levels of extensibility that might not be fully captured in what we're showing. So before we move on to talk about mutation history, just to try and avoid one dose of migraine medicine that everyone might have to take if they were serializing to and from XML, is just to point out a gotcha where we found that LabVIEW doesn't seamlessly handle the case where classes contain variants. This is something where basically if you have a non-null variant within class data and you serialize that to disk using the XML function, that will work just fine. If you try to then read it back with the same load function, LabVIEW will trip up over the XML that it created itself, and it will fail on that unflattening and parsing. So it can be a little bit tough to debug when you don't know why that's happening, and there seems to be no good reason why it should. But reasonable workaround is this isn't necessarily elegant, it gets the job done. You can, once you generate the XML, you can effectively nullify any variants that exist and store those as null variants, and then you'll be able to load data back in. This means that you can't use those variants to store meaningful data on disk, but if those variants are only intended to be used at runtime, then this is a workaround that avoids the flattening and unflattening variant issue. And for our case, we just needed those variants in certain runtime cases within the classes, but they weren't being used to just persistently store data on disk. So now we're going to talk about, we said XML allows us to leverage class mutation history. Who here is familiar with the idea of mutation history as it relates to classes? So only a handful of people. So good topic to talk about. The idea here is that you have a class and it, of course, has a cluster of class private data, but while we represent class data as a cluster, a class is, of course, much smarter and much, there's a lot more there than just being a cluster of data. And an important thing when it comes to managing configuration data is knowing that behind the scenes, LabVIEW tracks class mutation history. And so what this really means is that so basically, LabVIEW is continually tracking the evolution of a class and how the class's data changes over time. Now, you probably don't think about this too much when you're just running with a class in your application where you're just using it at runtime, because you're always running with the latest version of that class. And if you had an older version where you had different stuff in your class data, you don't care about that because all your code has been updated and molded to the newer version of the class, and something was broken in the block diagrams if your class data changed too much and you already fixed that. And you don't care too much about what your older versions of the class were. But when you start to save data last week and store that to disk, and then this week you've changed your class to do something newer and better and change the data, well, you might still consider that a valid set of configuration data that you want to load in, but it doesn't map exactly to your current class. And that's where you have different versions of the class. So LabVIEW does actually maintain different versions of the class. You can see that if you go to the properties of a class, version 1.001, 02, and so forth. It versions classes as the data changes. And when you have stored versions of older class data and then still want to use that, that's where mutation history comes into play. LabVIEW will basically keep track of certain things that happen over the life of that class and do migration handling of that for you. So what types of things does LabVIEW handle and track within mutation history? Well, it does track element name changes if you rename one of the items in class private data. It handles reordering of the elements in class data. It does handle basic coercible element data type changes. So if you change something from an integer to a double, it will be able to handle that kind of what would normally on the block diagram be a coercible data type change. If you had the number 10 stored there as an integer, it will be able to know that's the number 10 as a double. And it handles adding and removing elements fairly well. Perhaps more importantly, talking about what LabVIEW does not handle with mutation history, it definitely does not handle renaming of a class. It doesn't just only slightly not handle it. As far as LabVIEW is concerned, when you rename a class, it's important to know that LabVIEW considers that to be an entirely new class. LabVIEW will maintain no relationship of that new class name to whatever it might have previously been named. So if you have previously serialized class data in files, LabVIEW will not make an association or really try and parse that and load that in for you. So just means that when you, if possible, if you're using classes for config data, you need to name them the way they need to be up front. Use those names carefully so that you don't have to rename it later. Yeah, question?
Lesson learned. Don't put these classes in a library for your application.
Okay.
And then decide that you're going to upgrade your application by renaming that library. Because then you can't load the old files and the new files into the new application.
Okay, so you ran into that case. So,
for hard to transition.
so the class name is also dependent, the namespacing includes the library.
Namespacing the application.
Okay, and so that breaks the...
So put all the config file objects in a separate library, like just for config.
Yeah.
So if you want to update your application, you could reuse that library.
Yeah, that's a very good point. Yeah, good tip. So be careful about renaming a class. You can break existing config data. Other things that LabVIEW doesn't handle with mutation history is non-coercible data type changes. So if you have something that's a number and you change that same element to a string, it's not going to handle that mutation. It also doesn't handle clusters within class private data particularly well, and it doesn't handle enums within class private data particularly well. So for those last two items, we'll talk a little more about those and ways to gain better mutatability of classes. So if you had something that that you would consider having a cluster in your class private data, but you want better mutatability handling, you should consider converting that cluster to a class. And that's simply because that class might not have any methods or particular functionality associated with it. You could just use that class as a data construct and use it to take advantage of the fact that mutation history will then permeate down into that class. So all the same handling of element data type changes and renaming and reordering will permeate down into that class within a class. Whereas if you just had a cluster within a class and you rearrange and rename things in that cluster, you don't get the same realignment of those things that are stored in that cluster. And then finally, talking about enums within class private data. Essentially, these are typed enums. LabVIEW considers that kind of its own effectively unique data type. And if you store data with one version of that enum, subsequently want to load it up when your application and your latest code has a new modified, rearranged version of that enum with new elements or renamed elements, LabVIEW is not going to handle loading that very, very nicely. So a pretty simple workaround that has only small disadvantages as far as execution efficiency is to have the actual item in your class data be a string field. A string field that stores the string representation of that enum. And what you can do then is have read and write data member accessors, which you probably already would have. And within those accessors, do simple conversions from string to enum and enum to string. You then get the ability to handle changes to that enum that occur over time in a situation where that occur, so that you will basically, with the conversion from string to enum, you'll get the kind of expected correlation. If something still has the same name as it did before, it will load up with the same name. And if items weren't there, you won't have actual breakdowns of the parsing of the XML. And the other nice benefit is that you still use those data member accessors in any case where you're referring to that property. So aside from that single string to enum conversion, you're working with the enum, which is much nicer to work with, of course, throughout the application. And so you get the advantages of still having that property as an enum. Any questions on any of those save and load basic class methods?
So I'm going to talk about an issue regarding dependencies in your LabVIEW project. Everyone's seen the dependencies list at the bottom of your project for non-explicitly specified VIs or controls that are in your project. So dependencies are not bad, inherently bad. They're going to happen if you're going to have your sub-VI dependencies. You need sub-VIs to have good architecture in LabVIEW. You're going to have your control dependencies with your type defs as well. That's okay. And they really become a problem when they start growing out of proportion. The obvious implications for why that's bad is it's disorganization in your project. There's coupling throughout your project. There's lack of modularity, and it can lead to an unclear hierarchy in regards to object-oriented. The not obvious implications when talking about LabVIEW specifically is project load speed and compile time. So I'm going to talk about those two. To start, a class VI, or really a VI outside of a class that's just in your project, it has sub-VI dependencies, not class private data, and that's it. When inside of a class, you add class private data as a dependency, so that's controls in your class private data. All the VIs inside your class and controls inside the class are now dependencies, and that all of the class members inside of the parent or inside the hierarchy, the inheritance hierarchy, are also dependencies. So it's very prone to having a growing dependency tree, OO that is, as you develop your hierarchies. So the implications for load time, if you have a lot of dependencies in your project, it's necessary for LabVIEW to iterate through and load for each VI all of the dependencies for that VI. It's not necessarily an issue in LabVIEW actually loading. It's because you have so many dependencies in your project for your VI, it takes longer to load. And so this can happen when you're loading your project or when you're just loading a VI into memory. For compiling, I'm talking about compiling while you're editing, as well as your building. Compilation it's very similar. It has to iterate all the dependencies to determine the compilation. I can't claim to know the details of the compilation that LabVIEW does in the background, but with the growing dependencies, there's going to be longer compilation times when you're building as well as when you're editing. So troubleshooting dependencies in your project. This is a snippet from VI hierarchy. It's definitely the obvious way to go, or the first choice for trying to troubleshoot dependencies in your project. When I was working through dependency issues in some of our OO hierarchies, I found it a little cumbersome to navigate just because it's graphical, which is nice, but it can be difficult to actually navigate to the specific VI. I don't know if you guys have experience with that. So a trick, or it's kind of a simple thing that I did to troubleshoot, is actually just isolated classes that I thought were problematic and brought them into a target in a project and let LabVIEW decide what all the dependencies were. And then you had to be somewhat intelligent, or I had to be somewhat intelligent about figuring out what the problem dependencies were. So looking at the dependencies tree and saying, well, that class really shouldn't be a dependency of this class. And I want to challenge you guys to actually do this with some of your OO hierarchies. A VI that's called in a lot of different places that can make sense to be a part of a class can cause kind of a stratification or cascading of dependencies, and it's okay because it's part of the class, but you really want to make sure that you're not causing these really extraneous dependencies that shouldn't be in your project or in your hierarchy. So if you want to avoid this up front and not have to go into the VI hierarchy or kind of backtrack and look at where your dependencies are, two pretty easy things to do and that are official best practices in OO development. Enforcing VI scope. If you enforce your private scope on VIs that should be private, then you'll avoid having that called outside your class and then cause a dependency in that way. And then minimizing class VI's controls. I want to be clear about this. You don't want to just strip down your class to be as small as possible just based on this issue, or not issue, but trying to avoid dependency and minimize coupling. I'm trying to say you really want to be intelligent about what you're putting in your class. You don't want to put anything that you think is slightly related to your class into your class. You should be intelligent about it. So, question?
So,
You said a
on the
comment?
last slide, one thing that can get you into trouble is like, you've got a class, it has a type def, you send that type def, or use that type def across the network. Now, on the other side, you won't use the type def, which are multiple classes, they bring the type def part of the class. So it really helps if you make a library and a class. The class is the library is all the interface type defs.
You're saying
The class
library-
uses the
Library outside of the class? Yeah, that's a good point.
So if you split that up, it'll fix a lot of like cross network or cross application.
Yeah, that's a good point. The issues we were running into, they weren't necessarily for cross-application, but, so that's a good point to know.
If you have a control that really is not functionally, truly associated or should be a member of that class, if it's only lightly related, it happens to get used there, but also in a lot of other places, you don't want to include it in that class, because then anything else that controls, refers to that general purpose control is going to have that class as a dependency. And you have to be smart about properly selecting what is a actual member of your class library, and not just throwing stuff in there because, I need somewhere to put it. It can go in here. And there are a lot of rules and guidelines that you're going to do on what should or shouldn't functionally be included in the class.
Did I hear something back there?
I just asked to repeat the comment.
He was bringing up how for cross-application communication, correct me if I say this wrong, that if you have a type def inside a class and you try to use that cross-application, it will cause issues because it has to load all the other VIs in the class with that in memory. Correct?
The other target, which may not really use that class at all, will become dependent on that class and pull it in as a dependency of that other target's application.
That's a whole other thing we can
Killer
talk
is
about.
the status type def.
Yeah, something like that.
The status of the instrument, and now you have instrument dependency.
That's a big topic. It is how to manage your classes with your two targets. It's a good point.
Just put it in your interface project, which doesn't have a presentation.
Yeah, we agree. Yeah, we agree. All right, so organization. This is going to be a pretty quick slide. It's going to remnant. It's going to be remnant to best practices for NI, but we'd like to iterate it. There are two kind of organizations you can take for OO, or there are two aspects of organization. First is your project organization. This is your actual class organization and VI organization on disk. We've done an architecture where you create a folder for each class you have, and every child class folder is contained in the parent class's folder, and there are no folders for VIs or controls, so they're just open on disk. And so when you do that and you use auto-populating folder, is everyone familiar with auto-populating folder? Okay. It naturally follows a hierarchy in your project, so you really only have to maintain it on disk, and your project follows naturally. So the other aspect of organization is class organization. This is what your VIs are looking like inside your class. So we use virtual folders. We do not, like I said, we do not use folders on disk. And on the left, there is organization by functionality. So configuration, data member access is a very common one. That is good for navigation. It's really easy to quickly see where your VI could be. It's not really standardized among all your classes. It's hard to standardize by functionality across all your classes. You can do data member access and maybe utility, but it kind of just depends. So it's not consistent. On the right, you can organize by type. Not by type, by scope. So that's private, protected, and community if you're feeling crazy in public. That is standard across all classes, so it's really consistent, but it's not as easy to navigate because you're not quite sure where you put your VIs or controls. And you kind of see under public, we have configuration data member access. This is kind of what we've done, and it's worked pretty well. We actually organize within the scope folders, more virtual folders to organize by functionality. So you can kind of dig into each of the 4 scopes and yes, question?
How many methods do your typical classes have? Like 20, 10, 30?
Average, I would say 10, like 10.
Something like 10.
Do you need to read all those virtual folders for 10 methods?
Not really. I mean, this would just be a general.
It's just obscures reading the class composition.
That's true. If you have relatively few, which is going to be good if you don't try and overcomplicate and make your class do and create levels of classes to have more abstraction, then yes. I mean, this would be. I guess this example happened to be again our base class where we did have a little bit more in this class, probably closer to 30 methods, and then maybe 5. Maybe we've had vacuum in there. So.
That's a good point to make. I mean, if you have a class with 2 or 3 methods, because it's pretty simple, I would be hesitant to go into virtual folders to organize all those.
I'm a little confused on what you were saying before. You had, arranged your files on disk instead of auto-populating folders. This is not that. So you're saying there are 2 different ways?
Yeah, I mean, this is through virtual folders. So it's purely for LabVIEW and for you as a developer in your project to look at your. Are you wondering about the project organization? Or?
Yeah,
Sure, I can jump back to that.
I would never try to organize things on disk exactly the way that one appear in that tree.
There's 2 separate considerations that you can uniquely do. How are things actually present on disk? And the approach we recommended there is that the folder hierarchy on disk represents inheritance hierarchy. There is one folder for each class, and the containment of those folders aligns with class inheritance hierarchy. If you want to group a few methods within a class, maybe you don't create subfolders for those. The advantage is it lets you apply auto-populating folders in your project. It will load in a whole maybe directory of all your classes, and the auto-population will show a folder structure that mirrors the inheritance hierarchy, which makes it intuitive and nice to see that, in your project tree, that high-level folder structure, like what we see on the right, action with child classes of execute sequence element general action, mirrors the inheritance hierarchy. Then when you get into a class, you can use the virtual folders on the next slide to divide it up further if you happen to have enough in the class to warrant some organization.
We can talk afterwards if you want to talk one. So on the data member access, we're kind of running a long time, so I'll try to keep it fast. There are 2 ways to access your data for class private data. On your block diagram, you have your VIs and your property nodes. Everyone knows property nodes will call your data member accessor VIs, so there's kind of a dependency there. We have had a good time with property nodes. It's worked well for us. Kind of 3 things I can highlight on why we like those. It's organized. As you know, if you have maybe 10 properties you need to access at once and maybe they're not in a cluster, you're going to have 10 successive calls to a VI, and that can get, it's a lot of unnecessary code for your block diagram that can distract from the main purpose of your VI. Whereas property node, you can access them all in one spot in your block diagram. They are still searchable. This is just something to highlight. VIs are obviously searchable, but these property nodes are searchable as well. That's the main benefit of a data member accessor, is you can navigate to where you're destructing your data, and it helps with debugging and isolating your code.
A benefit along with just encapsulating the data, the main benefit
of
data member access.
Yeah. And then this is something unique to property nodes over VIs, is you can actually use a DVR on your connector pane, or a DVR into the property node, and it will automatically recognize it's a DVR, recognize what class is on the DVR or in the DVR, and it will automatically do essentially the in-place element that you have to do otherwise to access your data. And that implies it's also locking the data in the DVR down. Yeah, question?
I did that at one point, and there's a setting that you have to enable in your class properties in order for that to work.
There's a setting in your class properties that to allow creation of references outside of that class or use of references outside of that class. So I guess if you're trying to make a public, if you have a reference to your class that's being used outside of that class, and you want to use property nodes as a public accessor to that, then you're going to need to enable that setting. It's basically a question of whether you can have a reference to a class and interact with that outside of the class itself. Yep, question.
You're talking about this is to enable the property that you had issues that you create Accessor for your data integration.
Yes.
Sort of built in.
Yes. Yeah.
Yeah, this is like accessor function, just in the form of a focus name.
Yes, and the important point you made is that if you make a custom accessor where you add more code than just bundling and unbundling, and you make like that string to enum conversion method, there's a little bit of custom functionality. If you use a property node, it is a shortcut. It is just a different representation of a call to that accessor. So property nodes will call customized accessors that have more unique functionality than just bundling and unbundling within them.
To iterate again on the searchability, the bundling and unbundling are not searchable. So although it's allowed inside your class, it would be nice to be able to search even within your class where accessors are happening. Yes.
One comment, I think that if you find a lot of these nodes in your program, you've got the leak abstraction. You need to rethink your classes faster to design.
That's a really good architecture point. Did everyone hear that? He was saying if you start seeing a lot of these property nodes or even data member accessors throughout your program, you might want to rethink your abstraction. Was that the word you used?
Yeah, the class
Abstraction.
Oh,
Yeah. So 2 notes on properties, notable properties. The left is the default execution properties that LabVIEW does use for automatically created data member accessors. The only notable one is inlining. Inlining is basically copying the block diagram and putting it on the caller's block diagram. That's for execution speed. The goal with these data member accessors is execution speed, so that's why that's used. Because you inline, it actually overrides the reentrancy settings, so that's not important. On the top is a basic read accessor, and on the bottom is a write accessor. You'll notice the difference is the error case. That is because reading is not destructive. You may want to still access your data after an error occurs upstream, whether that's for reporting to actually get your data off the class or some other reason. It is okay to allow read of your data. Write, on the other hand, is you really don't want to write to your class if there's an upstream error.
And then note that read without the error structure is different than what LabVIEW will create by default for you. You probably know that. This is just something where, because it's not destructive, in a lot of cases we've chosen to eliminate an error structure. In case, you can selectively do this, but do it in cases where you maybe do want to make sure you still get the data for some other use versus null data if you have an upstream error. So it can be selective, but...
I'm going to come talk to us afterwards. I can talk about this dynamic accessor. I want to get to some of the tools that we have. So we discovered 2 pretty useful tools when doing OO development. This is just kind of development overhead that can be mitigated. There's a front panel utility and renaming labels. So the front panel cleanup tool, this is to resolve the issue that I think everyone has when doing LabVIEW development, where the front panel of your sub-VIs that are not shown to your user just go to hell and don't get taken care of. And that's fine. It would add too much development time to do it manually, but there's a hotkey that's provided by, I believe it's the, what did I say?
LNH.
Yeah, LNH Toolbox, Maker Hub Toolbox. That makes this easy. So it's in the quick drop, there's a hotkey. This is the default functionality. You can customize it if you like, and it turns it into this. It'll reorganize your icons or your controls and indicators on the front panel to match the connector pane, and it'll also resize the front panel to kind of size to fit. And then this is just side by side on before and after. So renaming labels, if you do have to unfortunately rename a class, it's a pain to go through all the static and dynamic accessors, or in layman's terms, just all the objects that are on the front panel, and update the label for those objects, because you should be naming them after your class in and out. And there's a script that uses VI scripting written by Lava to actually rename the labels if you do rename the class, or it basically updates all the labels to match the new class. So if you have a class like our base class with a lot of different methods in it, it could take a while to actually do that update. So if, let's say, NI, want to do NI objects, you can change it to this. You notice it's NI object, so DMC
You don't
object.
have to do it, it's just name classes object and object.
Sure, yeah. Is that what you do for
Yeah,
your class?
because I see the contents, I see the.
And you see the icon? That's
You
what
just
you
make
do.
sure to make the icon unique. You do take the time to edit the icon, but you keep the connector page
The
labels
icon, the
there.
file name,
Yeah.
it's prefixed by the class name.
Mhm.
Yeah.
So we just covered some ways you can manage your O hierarchies. If you have any questions, we actually are out of time for questions, but we can
We can stick around for a few minutes.
stick around. Yeah.
We'll have to-
Thanks for attending.